Hi everybody, my name is Rupa, working as Assistant Professor in Chevron Engineering College in the Department of Electrical and Electronics Engineering. I'm giving the subject renewable energy sources, and today's topic in this is estimation of energy power in a double basin tidal system. Okay, if you see this, So in previous we have seen that estimation of energy system in a simple single basin tidal system. So there we got that P average by P average by A is equal to, it is equal to around 0.225 R square watts. And now we see that estimation in the double power is work done is equal to, wait a minute. So actually it is not double, it is single now. After single, after this slide, now it is about single basin tidal system only. So this is the work done for single basin tidal system. So in previous classes we have learned about up to fifth equation. Now once again I am coming from fourth equation. So W is equal to limits from R to 0 dW. If you integrate, we will get 1 by 2 G rho A R square, and we know that average theoretical power is PAV is equal to work done by time, and work done is equal to here this formula, and time is, it is 6 hours 12.5 minutes. It is converted to 22,350 seconds, and if you substitute all the values known, we will get the average theoretical power 1 by 44,700 G rho A R square. So from this, if you assume an average sea water density as 1025 kgs per meter cube, then we can write the average power per unit basin area. It is P average is equal to 1 by 44,700 into, we are assuming that G, it is the gravity, sorry, average water density rho is 1025 kgs per meter cube, and G is 9.80, and here rho into A we are, sorry, A is here, 1 minute. See here, if you send this A to denominator of PA average, remaining are Z rho and R square. Okay, Z, this is Z, and this is rho, and R square is as it is. Okay, we are sending this A divided by PAV. So left side we are sending the right hand side. So remaining factor is 1 by 44,700 into Z. G means 9.80, rho means density 1025 kgs per meter cube, and into R square. We don't know the R square. So if you calculate all the numerical values here, 1 by 44,700 into 9.80 into 1025, you will get 0.225, and into R square, watts per meter square, or we can write megawatts per kilometer square. Okay, so this is the average power per unit basin. Okay, per single basin it is the average power. So P average by A per unit basin, that means A means here under denominator A means unit basin. Okay, so this is the actual power generated by a real tidal system. Okay, so actually the actual power generated will be less than the average theoretical power obtained from the above expressions, because there are some losses. First one is fractional loss, and second one is due to the conversion efficiencies of turbine and electrical generators, we are losing some energy. So due to these two losses, frictional losses and conversion losses, we are getting the actual power lower than the average theoretical power. Okay, so this actual power which is generated is about maybe about 25 to 30% of the theoretical power. Okay, so this is the estimation of average power in a single basin. Now we will go for double basin. So this is the estimation of energy in a double basin tidal system. So if you consider a double cycle system, this estimation of energy and power, these can be made as per usual calculations of power in the hydroelectric plant only. So whatever the calculations you are doing in the hydroelectric plant, same calculations we can be done in this double cycle system also. Okay, so but we are considering the average discharge and available head at any instant we are considering. Okay, so when we consider at this point of view, total energy can be obtained by integrating the value of instantaneous power. Okay, so the energy that is available for the tidal plant, it depends upon the first one is range of the tide, and second one is volumetric capacity of the basin. Okay, so what is the dependable factors that is available, that is dependable? First, the energy is available for the tidal plant, which depends upon first one, range of the tide. What is the range of the tide? Is it high or low? Okay. And second one is volumetric capacity of the basin. What is the volume of water present in the basin? It depends upon the energy. Okay. So the power from the plant, it is generally obtained in parts. Okay. In parts means in time durations it is obtained. So in duration of 3 to 3.5 hours in a flat tide cycle, and for equal duration in ebb cycles. Okay, both are considered in 3 to 3.5 hours in a flat tide cycle, and equal duration again 3 to 3.5 in ebb cycle. So and that means flowback cycle also. So these are approximately 705 full tide cycles in a year. Okay, so these can be evaluated as 705 full tidal cycles in a year. So from this, the power or total energy is first calculated per tidal cycle. First calculated per tidal cycle, the power, and then it is calculated for year. Okay, so for year, total energy can be obtained as below. So if you assume let V is the volume of the basin, then we can write V is equal to A into H naught, where here A is the average cross-sectional area of the basin in meters cube. Okay, so you know that A is simply area, and H naught, it is the maximum difference of the water levels. Okay, so that is the difference between the maximum water level and difference of the minimum water level. Okay, so if you both minus them, you will get, subtract them, you will get H naught. So it is the difference between maximum and minimum water levels. So from that, average discharge Q can be written as per time. Okay, so A H naught by time, per time, where T is the total duration of generation in one filling or in one emptying operation. Okay, so what is the time needed for full filling of the reservoir and full emptying of the reservoir? It is denoted as time T. So by these considerations, now power generated at any instant, power generation is equal to P is equal to rho QH by 75 into neta naught HP horsepower. So that is equal to, if you convert this horsepower into kilowatts, we can write into 0.76. So the conversion I have mentioned here, that is equal to rho QH by 75 into neta naught into 0.736 kilowatts. So Here we know that rho is the average density of seawater. So what is the value of rho? We have to remember this value is not given in the problems. We have to take our own by remembering the value. So rho is equal to 1025 kgs per meters cube. Okay, 1025 kgs per meter cube. And here H, it is the available heat at that instant. So here H is the water level difference, and here here H naught is the water level difference, and here H is the heat, available heat at that instant. Okay, so from these equations, the total energy can be integrated from limits 0 to time t. Okay, so 0 to t, p dt. What is the value of p? This one. Okay, so substitute the value of P here. Rho Q H by 75 meter naught into 0.736 kilowatts per tidal cycle. So this is the value per tidal cycle. Okay, and per year also we can calculate by per year. Okay, so the yearly power generation is P into dt here. So this is the yearly power generation. What is that? Same 0 to t per year we have to write here. Okay, per year. Here per tidal cycle here, and last per year we have to write here. So this is the, if you have to integrate the available head H, it is a function of time, and 0 to t H dt can be obtained graphically. Okay, 0 to t H dt can be obtained graphically. We can calculate the value of available H. Okay, so we will go through two problems. Before going to two problems, we will complete this theory part in two slides. First one is site requirements. So I am completing the theory part first. See, site requirements. So what are the site requirements for this construction of the tidal plants? So what are the considerations while we are selecting the site? We will see now. So that this utilization of tidal electric energy, it requires the construction of what is the needed ones, barriers across the narrow. Okay, so we have to require some barriers. These are located at the inlet to the estuary or bay. Okay, so these barriers forms a enclosure or something we call it as basin. Okay, so in this basin, ocean water are allowed, and electricity can be generated by allowing the water to flow through the turbine from the basin filled at high tide and to open the ocean during the falling tides. Okay, so we have to do this mechanism also. So while we are allowing the water to flow into the turbines, we have to open, and after falling onto the turbines, the water will be gone away to the oceans again. And again, the basin will be filled from the oceans during the rising tides. So this is the cyclic process. During the rising tides, the reservoir will be filled, and during the low tides, it will be emptied. So in each case, whatever the case we have discussed, in each case, the maximum amount of electrical energy it generated will be depending upon the product of tidal range R and the mass or nothing but volume of water flowing through the turbines. Okay, that Generation of electrical power will be depending upon the product of tidal range R and mass of water flowing through the turbine. So this volume is equal to range multiplied by the area of water in this basin. Okay, so volume is, again we can calculate the range. How to calculate means volume range into area of water in pounding. We will get the range. So hence finally the total electrical energy is proportional to the square of the range and area of the basin. So from the equations we came to know that the total electrical energy is proportional to the square of the range and area of the enclosed basin. So a favorable site for the tidal power plant should have a large tidal range. And the geographic features should permit enclosing of large areas with reasonably short dams, or other barrages which are enclosed short should have low areas. Okay, so this sluice gates in the dams, we know that sluice gates means nothing but opening and closing of the gates. So these are called as sluice gates. So these sluice gates in the dams permit water to pass or from the enclosed basin. Okay, to or fro from the enclosed basin, pass waters and allow waters to go away. These are the site requirements of the tidal power plant. And next last one is storage. So this storage is done by 4 methods. So before going to these 4 methods, we will complete some introduction. So actually storage, why it is necessary means when an alternative electricity production schemes are not there with this tidal power plant, we have to store when it is in peak production, and we have to deliver this when at the times of peak demand, right? So if you are not connecting any to the other electrical production systems, this storage is important. Okay, and if this is not connected, we cannot, if it is not connected to any other electricity production scheme, we cannot connect this only, we cannot connect this tidal electrical generation to the grid directly, because grid means it should compulsory have continuous power flow, and depending upon this only tidal power ranges and depending upon the tidal power plant, grid cannot work. So only tidal power plant alone cannot be connected to the grid. If you are taking other connecting schemes, other electricity production schemes, then we can definitely connect this tidal power plant to the grid, because tidal power plants are not exceptional to this rule, because there is a strong case for associating that storage will be provided for varying needs of the customers, and we have to take in account also close of other plants also. So this power plant has by its very nature many of the components required of a pumped storage scheme. It also have an advantage with a scheme that added tidal power becomes a firm daytime source of power. We can give more energy at the daytime source of power, so it is becoming a added power. So this is an important principle, because saving provided by tidal energy is that of fuel, and probably it is of not pollution, and cost will also be reduced. So the fuel saved depends upon the type of plant whose load factor is reduced, and we are additionally taking the tidal power plant without it. Okay, so the alternate to store when the energy is available, but power is not needed because of timing, it is to generate, and but it is potentially left untapped, it is not recoverable at that time. Okay, so we have to store energy because it is not recoverable at that time. So if you store it for we have to, if you store, we can give it in future when the demand is more. So for this storing also, we have to put some extra capital investment. Okay, so for this tidal power, it is produced in mechanical form. Okay, so as it is produced in mechanical form, only batteries, compressed air, hydraulic storage is considered. So what is the form of tidal power? It is of mechanical form. Okay, so flywheel can be used, but flywheel storage can be used, but it is not at ready at present. So how to store means flywheel storage. First one, if you connect a flywheel to the motor or generator, it is spinned up to a high speed and it absorbs energy. Okay, so this energy can be again reversed to the motor or generator by decreasing the flywheel speed. Okay, so by this is a free, this is a costless free of storing the energy, but it is only in small quantities we can store. Okay, and in small quantities and in short periods of time only we can store this flywheel. And second one is battery storage. Okay, second one is battery storage. It is the most flexible and practical electrochemical battery we are using here. Okay, so these batteries are most common, but research is also being conducted in this. Okay, so what is the research conducted means, with less expensive and lighter weights of batteries, we can store this energy or not. Okay, so present available are aqueous solutions like nickel and nickel cadmium types. Okay, nickel with made of nickel and nickel cadmium types, but these nickel is most costliest, so the battery will also be costly. Okay, and this type of storage, it is suited only to small plants, particularly self-contained ones. Okay, next last one is hydraulic storage. Sorry, third one is hydraulic storage. This hydraulic, that is nothing but pumped water, or we can call it as pumped water. Okay, so this hydraulic or pumped water storage, it is most frequently mentioned in the connection with the tidal power plants. Suppose if you take two reservoirs at different elevations, these are linked by pumps and turbines and then motors and generators. So this contains the accumulator, nothing but a reversible pump turbine which is connected to the motor and generator. It achieves the same result. Okay, so off peak energy which could be used, it is put into work to the pump water from the lower into the upper reservoir, which can run through the turbine and generator, and this provide energy when needed at the later times. Okay, so power can be provided immediately on demand with this type of hydraulic storage, and storage stabilizes and otherwise storage stabilizes otherwise a intermittent source, and it has an efficiency improvement also. Okay, so for this we have to find some reservoirs and they have to be built, and we by transforming this to pumping water, certainly we can lose some amount of energy to activate the work and pump. And last one is compressed air storage. Okay, in this is a simple procedure. Air is compressed during off peak periods. Okay, and this compressed air is stored underground. When the requirement is there, it is called upon. Okay, so it is called upon to work for the gas turbines, and these provide the electricity. So tidal energy can be used directly to drive a 8 turbo compressors. Okay. So this is the theory part of the first chapter in this. So tidal part is over. We have two problems now. We will see. So first one, a tidal power plant sorry. So first one, the observed difference between the high and low water tide is 8.5 meters. Okay. So the difference between the maximum and minimum limit of water tide is 8.5 meters. That means H naught. It is the difference of the maximum and minimum limits. H naught is 8.5 meters for a proposed tile site. Okay, so the basin area is about 0.5 square kilometers. This is 0.5 square kilometers, which can generate power for 3 hours in each cycle. The average available head is assumed to be 8 meters and the overall efficiency of the generation will be 70%. Now calculate the power in HP at any instant and the yearly power output. Average specific weight of the sea water is assumed to be 1025 kgs per meter square. This is the value of rho. Okay, so now we have to find out at last power per annum. Okay, so first for this we have to find out the power at any instant. So power P at any instant is equal to, we know the formula Q rho H by 75 eta naught HP. We should find out the power in HP because they have asked. Find out the power in HP, horsepower. See. Okay, so for this we have to calculate Q and rho is given as 1025 and H is given. H we have to calculate heat. Sorry, given assume it to be 8 meters. It is given 8 H and 75 and eta naught is efficiency. They have given up to 70%. So in this we have to calculate only Q. Okay, so for calculating the Q formula is A H naught by T. Okay, so for this we have to calculate A, H naught and T. So A is given as area 0.5 square kilometers. So I am calculating this expression A into H naught. See A into H naught here. A is 0.5 square kilometers. That is square kilometers means 10 power 3, 10 power 3. Meters we have to convert. In kilometers we have to convert into meters. So kilo means square kilometers means 2 times K. So 10 power 3, 10 power 3, 10 power 6 total. Into H naught. H naught is given as 8.5. The difference between the maximum and minimum levels. It is 8.5 meters. So 8.5. We will get 4.25 into 10 power 6 meters cube. AH value. AH naught value. So divided by time. So time is given for 3 hours. Again we have to convert this into seconds. So 3 into 3600 seconds gives total value of seconds. So 4.25 into 10 power 6 divided by time. We will get 0.03704 into 10 power 6. So finally we can write 393.5 meters cube per second. So if you this is the value of Q obtained from this. If you substitute the value of Q here, 393.5 into 10 power, this is the rho value and this is H value 8 divided by 75 as is into neta efficiency 0.70. We will get the answer in HP. 310.15 into 10 square HP. So this is the power in HP at any instant. And we have to calculate the yearly power output. So for this, the total energy kWh E is equal to, we know that E is equal to P into 0.736 into 3 hours time. Okay. Here E is equal to, what is the formula of E here? 0 yearly power. Before E is given as QPH by 75 newton naught HP into 0.75 into 7 into number of times T. Sorry, 3 hours T. Okay, so we will get the energy here. Okay, here 0.736 is converting of HP into kilowatts. If you convert the HP value into kilowatts, you will get the energy. So for converting the HP into kilowatts, we have to multiply by 0.736. So this is the formula in HP. For converting into kilowatts, we are multiplying into 736. Okay, so hours taken is 3. So this is the total number of tidal cycles. Sorry, E is the energy per tidal cycle. Total energy per tidal cycle is this one. If you multiply the value into 0.736 into 3, we will get 664.93 10 square. So averagely we can know that number of tidal cycles in a year is 705. We have to remember this. Okay, we have to remember this value. Okay, so after getting the total energy per tidal cycle, if we want to yield this total energy per annum, we have to multiply into 705, because this is the standard value. Total number of tidal cycle in a year is 705. So if you multiply this value with the 705, we will get the value per year. This is per tidal cycle, per year means into 705. Okay, next, second problem. A tidal power plant of a simple single basin type has a basin area of A is equal to 30 into 10 power 6 meter square. Directly it is given in meter square. So no need to convert. Square kilometers or 10 power 6 meter square, both are same. So if the area is given in square kilometer square, we have to convert it into again this form only. K will be converted, K will be multiplied 2 times. So 10 power 3 becomes 10 power 6 meter square. Okay. And the tide has a range of 12 meters. The turbine, however, stops operating when the head on it falls below 3 meters. So this is the high tidal range. This is the low tidal range. Calculate the energy generated in one filling or emptying process. Okay, so energy generated in one filling or emptying process, calculate the energy in kilowatt hours. So we have to calculate this in kilowatt hours. If the turbine generator efficiency is 0.73%. Okay, so see, now we have to calculate W, P average and average power generated. We have to calculate these three. Okay, so first for theoretical work, we know that W is equal to R, maximum level range, minimum level range. So maximum is 12 and minimum is 3. So if you integrate the work energy done, we will get the answer. So R is equal to maximum minimum range minus work done, that is minus G rho A H DH. Okay, we can write this as minus G rho A. It is a constant term, so I'm keeping that forward the integration. Constants and remaining H DH I am integrating. So see, R square minus R square. 1 by 2 R square minus R square, 1 by 2 H square, minus 1 by 2 H square we will get. Minus minus cancel, 1 by 2 here. So remaining G rho A If you apply the limits r square minus r square h square